All right, we actually have a few slides remaining from the previous lecture. So let me finish those up before we move on to something new. So I wanted to talk a little bit about the embryonic development of the abdomen, similar to what I did with the thorax. I think it's particularly important to understand the embryonic development in the abdomen, to understand the relationships of something called the peritoneum, which is a membrane very similar to the pleura that we saw up in the thorax, and also to understand the formation of what are called the mesenteries and things like the greater and lesser omentum. So here's our simplified picture of the early human embryo again. Basically just, essentially a tube inside a tube is the way some people have described it. You've got the tube-shaped embryo, you've got the gut tube beginning at the mouth and continuing to the anus, and early in development, basically just a straight tube all the way from the mouth to the anus. There's that little pouch with the respiratory system beginning to pouch off the gut. But in talking about the development of the abdomen, rather than looking at a cut section, of course, through the thorax, we're going to make a cut section a little bit more caudally. In the case of the embryo here, we say caudal because it's closer to the tail end. But if you imagine this in the adult person, this would be more inferior, so down in the abdomen. So you see this cross section, very similar to what you saw before with the cut section through the thorax. So we've got the body of the embryo with the developing spinal cord dorsally, the aorta just anterior to that or ventral to that, and then the gut tube just anterior or ventral to both the spinal cord and the aorta. And then very similar to what we saw in the thorax, these cavities begin to develop in the wall of the embryo, in the body of the embryo. Now in the thorax, these were called pleural cavities, and they were lined with a membrane called pleura. Here in the abdomen, we call them peritoneal cavities, and they're lined with a very similar membrane, but just because it's in a different location, we give it a different name. It's called the peritoneum. Then later in development, those peritoneal cavities enlarge really significantly to occupy most of the area, most of the space of the abdomen. And just like we saw in the thorax, that membrane, that peritoneum, continues to line the inside of that cavity. Some of that peritoneum lines the inside of the abdominal wall, as well as the posterior abdominal wall, and we refer to that as parietal peritoneum, just like the parietal pleura in the thorax. And then some of that peritoneum ends up lining the surface of all of the organs of the gut, including all of the organs that are derived from the gut, which would include the stomach, the small intestine, the colon, but even things like the liver, the spleen, gallbladder, pancreas, and so forth are going to be lined with a layer of visceral peritoneum, again, analogous to the visceral pleura that lines the surface of the lungs. But something different that we have here in the abdomen that we didn't really have in the thorax is there are places posterior to the gut tube where those two layers of peritoneum actually come together and meet, and they form something called a mesentery. It's a double layer of peritoneum that is essentially anchoring the gut tube to the posterior abdominal wall. And it's formed from these two layers of mesentery, these two layers of peritoneum from the left and right peritoneal cavities. And then we see the same thing anteriorly, that the two layers of peritoneum have come together to form an anterior mesentery that is anchoring the gut tube to the inside of the anterior abdominal wall. Notice something else on here, that inside the posterior mesentery are all of the nerves and arteries that are supplying the structures of the gut. So in order for nerve supply and blood supply to reach the gut tube, early on in the embryo, and then the derivatives of that gut tube later in development, all of those nerves and arteries have to pass through this posterior mesentery. in order to reach the gut. And we'll see that that's true even in the adult, that there are remnants of these mesenteries and all of the nerves and arteries that are reaching the digestive organs are actually passing through these mesenteries in order to reach those organs. Right, now here's that same embryo at a little bit later stage in development. And if you look inside the abdomen of the embryo, you can see that that simple straight gut tube has started to become modified to give rise to a lot of the organs of the digestive system in the abdomen. So the gut tube itself has started to fold. It's made a turn here, kind of a fold to form the stomach. It begins to fold significantly to form the small intestine, and then also the large intestine, the colon. These are basically just, derivatives of that gut tube that just becomes longer and longer and longer and has to fold on itself in order to fit within the abdominal cavity. But there are other organs that develop as outpouchings of the gut tube, similar to the way that the trachea and the lungs formed as a little pouch that branched off of the upper end of the gut tube. The liver and the gallbladder and the whole biliary system, all the bile ducts and everything, this actually develops as just a little pouch, little side branch off of the gut tube. There's this little skinny thing here just behind the stomach. That's the pancreas. The pancreas also develops as just a little pouch off of the gut tube, which then branches and branches and branches and branches, and then gives rise to the cells that actually make up the pancreas itself. There's another structure up here that sits posterior to the stomach or dorsal to the stomach. That's the spleen. That's not really an outpouching of the gut tube, but it also develops in relationship to these other organs. The purple, that pale purple that you see up here in this side view of the embryo, that represents where these mesenteries are still found in the developing embryo. Notice that pale purple area runs the entire length of the gut tube on the dorsal or posterior aspect of the gut tube. And this persists into the adult, where you have a posterior mesentery that still connects all of the abdominal organs to the posterior abdominal wall. But if you go back to the previous slide, you'll see that in addition to that posterior mesentery, which is also carrying the blood and nerve supply, at an early stage of embryonic development, there's also an anterior mesentery where the two layers of peritoneum came together anterior to the gut. And that still remains only in the upper part, the more proximal part of the digestive tract, where there's a remnant of that anterior mesentery that sits anterior to the stomach and actually connects the stomach and even connects the duodenum to the liver and the gallbladder. And then the liver itself is connected to the anterior abdominal wall. So those are all remnants of the anterior part of the mesentery. But then posterior or inferior to the end of the liver, the entire anterior part of the mesentery disappears. Basically, the anterior mesentery basically just breaks through to create a gap, anterior to the digestive organs. So the fact that it's illustrated as being white here just indicates the fact that that anterior mesentery has been lost, basically from the liver and duodenum down, through the entire small intestine and the colon as well. The dotted line here indicates a level of cross-section. And again, we see that cross-section down here at the bottom. And this curving, waving line here, extending from the posterior abdominal wall, making a fold that heads over towards the spleen, and then another big fold where it folds back on itself and then connects to the stomach. All of that is part of that posterior mesentery. It's just become very modified later in development. But that was basically just that double layer of peritoneum connecting the organs of the gut tube to the posterior abdominal wall. It's just become much longer and folded in a complex way. Part of that posterior mesentery ends up folding back on itself to form this great big flap called the greater omentum. It looks basically like a big apron of fatty tissue that hangs off of the stomach and kind of lays over most of the abdominal organs. But it's derived from this big fold of that posterior mesentery. Now, remember that the mesentery itself forms from two layers of peritoneum, where the peritoneum from the left peritoneal cavity and the peritoneum from the right peritoneal cavity, they come together to form a mesentery. When this mesentery folds back on itself, it's a double layer of mesentery, but that means it's also 4 layers of peritoneum all sandwiched together. So if you look closely at the slide, you'll see that there's 4 purple lines there, 4 little purple lines. Each purple line represents a single layer of peritoneum. Now then, off of the anterior aspect of the stomach is another mesentery, which is part of the anterior mesentery. So this is what was connecting the gut tube to the inside of the anterior abdominal wall. And the entire liver and gallbladder and all of the bile ducts have actually formed within that anterior mesentery. But that's basically a remnant of the connection of that gut tube to the anterior abdominal wall. Now, something else that's shown on this slide is that as these abdominal organs continue to develop in the embryo and in the fetus, the liver begins to migrate towards the right side of the body. It actually starts its development sitting anterior to the stomach, close to the anterior abdominal wall, but it gradually begins to migrate over towards the right side of the body, which is on the left side of the slide here. Liver's migrating over to the right, which is where it ends up in the adult. Most of the liver is over on the right side of the abdomen. And as the liver is migrating to the right, what happens is that what used to be the right half of the peritoneal cavity, or the right peritoneal cavity, let me go back to this picture. You see that earlier in development, you had a left and right peritoneal cavities that were basically identical. They were mirror images of one another. But as the liver migrates over to the right side of the body, the right side of the peritoneal cavity becomes smaller and smaller and smaller. And eventually, by the time you reach adulthood, there's very little left of that right half of the peritoneal cavity. It's just a small area known as the omental bursa, which is trapped posterior to the stomach and the liver. The left side of the peritoneal cavity gets progressively bigger and bigger. So most of the abdominal cavity is actually consisting of the left side of the peritoneal cavity, which is gradually enlarged, whereas that lesser sac, the remnant of the right side, becomes very, very small and essentially trapped behind the liver and gallbladder. So in this later embryo, where the various abdominal organs have begun to develop, if we were to do another cross-section a little bit more posteriorly through the level of the small intestine, what you find is that the small intestine, as it elongates, it doesn't have room for it to just get, longer and longer and longer. It has to fold on itself. And so if you look at the cross-sectional view down here at the bottom, what I'm trying to show here is that we've still got that posterior mesentery, which is anchoring all of the remnants of the gut tube to the posterior abdominal wall. But as the intestine itself continues to fold back on itself, kind of zigzagging back and forth, that mesentery becomes very folded as well, almost like an accordion, folded up. So even in the adult, that posterior mesentery is still there, anchoring the intestines to the posterior abdominal wall. In fact, anchoring all of the organs of the gut to the posterior abdominal wall. And the nerve and blood supply to those different organs is traveling through that posterior mesentery in order to supply blood and nerve supply to those organs. This is something that I get a kick out of whenever you see any kind of popular representation of the intestines. People seem to have this impression that the intestines are just like a whole bunch of sausage links that are just kind of dumped into your intestine. And if somehow your abdomen is cut open, they're just going to spill out onto the ground like a bunch of sausage links. And there's a couple movies I can think of that depict this inaccurately. One of the Hannibal Lecter movies, I think it was the one actually called Hannibal. So the sequel to Silence of the Lambs. There's this Italian detective who's trying to hunt down Hannibal Lecter, and instead Hannibal Lecter kind of turns the tables on him, captures him, ties him to like a two-wheel dolly, and wheels him out onto a balcony, like in Rome, some closet in Rome or something. Puts a noose around his neck, cuts open his anterior abdominal wall, and then pushes him off the balcony, and he drops. The noose tightens up, the guy gets hung, but because his abdomen has been cut open, his intestines just spill out like a bunch of sausages on the sidewalk below. Doesn't do that. Same thing. Anybody see the movie Cocaine Bear? Anybody even heard of the movie Cocaine Bear? I saw it. I actually loved it. I thought it was hysterical. But especially the part at the end where Ray Liotta's character is getting eaten, and the mama bear brings the little bear cubs over, and they're like pulling his intestines out of his abdomen. And again, it's like the bears are running off with links of sausage. It's like, they don't do that. It's like, if you open up somebody's abdomen, you'll see it in the lab today. You try to pull out their intestines, they just go. They'd come out maybe a few inches and they'd stop.
Everybody tries to.
Because that posterior mesentery is only 8 or 10 inches long. And so it's only going to allow the intestines to come out just a tiny bit.
So the question is,
Yeah.
the folding pattern of everybody's small intestine identical, or is it?
No, the folding pattern of everybody's small intestine is not identical. In fact, the folding pattern of your small intestine is different now than it was 10 minutes ago. They're constantly moving.
Can you feel it?
You can. I think if you have some kind of gastrointestinal upset and a lot of gas, you might be able to sense that movement. You can certainly hear it,
So if
although what you're hearing is more like the gas moving around
if you're
inside.
drawing the small, like the abdominal organs, you can just sort of make it up with the folds of the small intestine.
Pretty much, yeah. The exact folding of that small intestine can be very random.
Well, even if you, one is so that it's like what you were saying about like how they don't just like spew out. They're all attached by the lesser omentum anyways, right? So like, it's really not like they would flop, you know what I mean?
The only attachment of the small intestine is by the mesentery attaching them to the posterior abdominal wall. So the lesser omentum specifically only connects the underside of the liver to the lesser curvature of the stomach and the first part of the body. That's all the lesser omentum. You may be thinking of greater omentum, the big fatty apron that hangs over the intestines.
Apron, but I thought that there was like along the small intestine, there's tissue that attaches.
That's the mesentery in the back that's anchoring the intestine to the posterior abdominal wall. Yep. All right, one more concept that I want to get across that's related to this embryonic development, but before we move on to the next lecture, are the relationships of different organs in the peritoneal cavity, where they're essentially located relative to the peritoneum. So if we look at that same picture that we just saw on the previous slide, we've got our cross-section through the developing embryo here. We've got, all these folds of small intestine that are anchored to the posterior abdominal wall by a mesentery with all of the nerve and blood supply. There are some structures in the abdomen that we refer to as being primary retroperitoneal structures. The word retroperitoneal means behind the peritoneum. So in a sense, really it means behind or posterior to the peritoneal cavities. And the word primary means that essentially they've been this way all along. They've been retroperitoneal since the beginning and have always and will always be retroperitoneal. So things like the kidneys. The kidneys are never hanging in the abdominal cavity. The kidneys always lie completely posterior to the two peritoneal cavities. So we refer to them as primary retroperitoneal structures. They've always been behind the peritoneum. The aorta would be another example, and the inferior vena cava next to it would be examples of structures that have always developed posterior to the peritoneal cavities. They're never hanging inside the abdomen. Then there are other structures that are always kind of free within the abdomen, although they're still anchored to the posterior abdominal wall by a mesentery. We refer to these things as intraperitoneal structures. So that an entire small intestine that we were just talking about, it's free to move around, which is why the exact folding pattern varies even from minute to minute. But they're still firmly anchored to the posterior abdominal wall, but they're basically free to move around in the abdomen, to the extent that the mesentery lets them move around. So you can think of them as basically hanging by mesentery within the peritoneal cavity. And then finally, there are some other structures that start their development as intraperitoneal structures. So they start out basically sort of hanging within the abdominal cavity, anchored to the posterior abdominal wall by a mesentery. But during embryonic development, these organs then will migrate over towards one of the abdominal walls, either to the left or the right abdominal wall, or sometimes even migrating posteriorly towards the posterior abdominal wall. And these organs will then fuse with the inside of the peritoneal cavity. They'll fuse with the inside of the abdominal wall. And their mesenteries that used to be anchoring them to the posterior abdominal wall, even those mesenteries will actually press right up against the inside of the peritoneal cavity and essentially fuse with the wall of the abdominal cavity. So we call these things secondary retroperitoneal structures. They started out intraperitoneal, but then later in development, they became retroperitoneal by migrating over and fusing with one of the abdominal walls. So examples of things that are secondarily retroperitoneal include things like the duodenum and the pancreas, which end up fused to the posterior abdominal wall. Originally, they were kind of free to move around a little bit and anchored by a mesentery, but then the organs and their mesentery fused to the posterior wall. The ascending colon, which is on the right-hand side, that part of the colon used to be free floating within the abdomen, but then fused to the inside of the abdominal wall on the right. Same thing with the descending colon on the left. It's fused to the inside of the abdominal cavity on the left. Okay, let's move on to the organs themselves. Right, so today what you're going to do in lab is you're going to open up the abdominal cavity, and we're going to use what's called the quadrant approach, where you're basically just going to make a vertical incision along the linea alba. Remember to stay just to the left of the umbilicus, though, as you cut down through that linea alba. And then you're going to make two transverse cuts, basically from the level of the umbilicus, transverse cuts laterally towards the side of the abdomen. And this will give you 4 flaps of anterior abdominal wall that you can then reflect out of the way and start looking at the organs inside the abdominal cavity. And you will literally pull on the small intestines and try to lift them up out of the abdominal cavity and just kind of work your way along them and kind of follow the length of the small intestine from beginning to end. So you'll be looking at all of these different organs. So what I want to do is walk you through the different organs of the abdomen, basically from beginning to end, from the first remnants of the gut tube all the way to the rectum. So from stomach through small intestine, colon, and rectum. And then we'll also talk about some of the accessory organs like liver, gallbladder, and pancreas and spleen. So here, of course, is the stomach. You've got the esophagus that's coming down through the diaphragm and poking through what's known as the esophageal hiatus, just a gap in the diaphragm. And the esophagus then enters into the stomach. The point where the esophagus enters the stomach is known as the cardia, named for its close proximity to the heart. The heart sits right above the diaphragm, right in this same area. And there's a little valve in there, sometimes called the cardiac valve or just the esophageal valve. Then there's part of the stomach that forms this large rounded dome that sits off to the left side of the body. And this would be sitting under the dome of the diaphragm on the left. This is known as the fundus. Anytime you have any organ that has a rounded top to it, it's always called a fundus. Gallbladder has a fundus, the uterus has a fundus, and the stomach has a fundus. Then the bulk of the stomach is known as the body. The body then narrows into this sort of funnel-shaped area known as the pylorus or the pyloric antrum. The pylorus itself is where you'd find the pyloric valve or pyloric sphincter. And we'll see on the next slide a cutaway view of this. So you see that there's a strong muscular sphincter down here that regulates the flow of food from the stomach into the first part of the duodenum. The overall shape of the stomach has these two curves. On the outside, facing towards the left side of the body and also facing inferiorly, is this big broad curve known as the greater curvature. And then on the right and kind of superior aspect of the stomach, you have a smaller, tighter curvature known as the lesser curve. So functionally, the stomach is basically just a big bag of muscle that's involved in churning the food, kind of mixing the food. And also the stomach secretes stomach acid and digestive enzymes. And that muscular churning motion just helps to mix the food with the stomach acid and with the digestive enzymes to improve the efficiency of digestion. If you cut into the stomach in a coronal plane, you see the esophagus again coming down to enter the cardia of the stomach, and there's that cardiac orifice. The fundus, the big dome extending up towards the left under the diaphragm, the body of the stomach, the pyloric antrum, basically this little funnel-shaped area that's leading to the narrow pylorus. And there's the pyloric sphincter, which is a muscular valve that regulates the flow of food from the stomach into the first part of the duodenum. The interior of the stomach is lined with these very distinctive ridges known as rugae. Next week, I believe it is, you'll actually be cutting into the stomach and looking for these rugae, although don't be surprised if you don't have real nice distinctive rugae, because sometimes after death, when all the muscles relax, you don't really see the rugae very well. But hopefully we'll see some. The next derivative of the gut tube, basically going from head to toe, the next structure that food would flow into is the duodenum. The duodenum is sometimes illustrated as just being kind of C-shaped, but it's not really C-shaped. I like to think of it as looking more like a big capital letter G. And it's actually more kind of squared off. And I've always thought it kind of looked like a little bit like a box because it has more of a horizontal superior part and more of a vertical part here that's straight up and down, and then another horizontal part, and then it comes up vertically again on the other side. So it's almost like a big square shape, really. So there are four parts to the duodenum. The superior part is the very first part, right after the pyloric sphincter coming from the stomach. This then makes a fairly sharp turn inferiorly to become the descending part of the duodenum, makes another sharp turn towards the left side of the body to form the horizontal part, and then it turns again superiorly to become the ascending part. And then that ascending part then joins with the next part of the small intestine, which would be the jejunum. The entire duodenum is considered a secondary retroperitoneal structure. So along with the stomach and the small intestine, this used to be sort of free moving within the abdomen, anchored to the posterior abdominal wall by a mesentery. But then later in development, the whole thing, along with the pancreas that sits kind of, that's surrounded by the duodenum, that whole area became fused to the posterior abdominal wall. So what that means is that the duodenum is going to be a little hard for you to see today in the lab because it's very far posteriorly and it is fused to the posterior abdominal wall. So you may be able to see the superior part, which is, just beyond the end of the stomach, but you may have trouble seeing the other parts of it. We'll come back to this later when we talk about the pancreas and the gallbladder and the bile ducts, but all of those ducts are actually entering the digestive tract through the descending part of the duodenum. So there are little openings that allow the ducts from the pancreas to flow into the duodenum, as well as the bile coming from the liver and gallbladder to flow into the duodenum. Here's a cut section through the duodenum. So you see the superior part up here that sits just beyond the pyloric sphincter. Then it turns inferiorly to become the descending part. You can actually see there's something here called the major duodenal papilla. It looks like like a tiny little fingertip or a tiny little nose protruding into the space, the lumen of the duodenum. And this is where both the bile duct and the pancreatic duct are draining into the duodenum. Then you reach the horizontal portion here, and then the ascending portion that then leads into the jejunum, which is the next part of the small intestine. The interior of the duodenum is lined with these circular folds called plicae circularis, which literally means circular folds. And we'll see that those plicae circularis continue throughout the entire length of the small intestine, the jejunum and the ileum, which are the two next parts. So after the duodenum, food would then flow into the jejunum, which is the second part of the small intestine, makes up about 2/5 of the total length. And I should have looked this up. I forget the details, but I mean, there's many feet of intestine. I think it's like 20 feet of intestine. So this would represent about 2/5 of that total length of the small intestine. And the whole small intestine is involved primarily in the absorption of nutrients. So some of the process of digestion continues, although the small intestine is not secreting additional digestive enzymes. All of the digestive enzymes are secreted by things like the stomach and the pancreas. So the process of digestion may continue in the small intestine, but the main function of the small intestine is then to absorb those nutrients that are released through the digestion of food, through the breakdown of food. The small intestine has several different layers. So this is true of the duodenum, the jejunum, and the ileum all have these same layers. There's an inner layer known as the mucosa. So this is just the mucous membrane on the interior of the intestine. And this is where you find those plicae circularis or circular folds. The plicae circularis are there to simply increase the surface area of the mucous membranes to increase the surface area that's available for the absorption of nutrients. Just outside of the mucosa is the submucosa, and this is where you find lots of little tiny capillaries, which are the vessels that are then going to absorb those nutrients into the bloodstream. Outside of the submucosa are two layers of muscles. There's an inner layer of circular muscle fibers, and then an outer layer of longitudinal muscle fibers that are running the whole length of the digestive tract. We actually saw some of this way up in the pharynx. The pharyngeal constrictor muscles actually represent the beginning of these circular muscle fibers. And then as the pharynx transitions to the esophagus, then the longitudinal fibers are then added onto the outside of that. And those longitudinal fibers run the whole length of the digestive tract, all the way from the beginnings of the esophagus, all the way to the anus. And then the outermost layer of tissue in the wall of the jejunum, and really the whole small intestine, is called the serosa. This is actually continuous with the mesentery. The serosa is really the visceral peritoneum. It's the layer of peritoneum that's lining the surface of the organ. And then that visceral peritoneum that's covering the organ is continuous with the two layers of peritoneum that make up the mesentery. And you see the mesentery up here, which is this membrane this double layer of peritoneum that's anchoring the organs to the posterior abdominal wall. And you can see that there are blood vessels in there because the blood supply and the nerve supply to the organ has to travel through that mesentery. Next section of small intestine is the ileum. This makes up about 3/5 of the length of the small intestine, so it's a little longer than the jejunum. Has the same layers. You see the mucosa. Now, in this illustration, you don't really see a lot of plicae circularis. In fact, there really aren't any plicae circularis evident here. You don't have any of those circular folds. Supposedly, that's one of the key differences between jejunum and ileum, that the jejunum has a lot of plicae circularis and the ileum doesn't. But two things about that. Number one, in all of the cadavers I've dissected, I could never tell you that that's really true. I see plicae circularis all the way the whole length of the ileum in most of the cadavers that I've dissected. The other thing is that even if there is a difference, that the jejunum has more plicae and the ileum has less, it's not like there's an abrupt change. It's not like, oh, you hit the beginning of the ileum and all of a sudden all the plicae circularis go away. If there is a difference, it's a very gradual, subtle change from one to the other. All right, so after the small intestine, food is going to then flow into the large intestine, more properly known as the colon. And the colon has many different parts to it, as well as a lot of important landmarks and structures. So what you're seeing over here is the very end of the ileum, the very end of the last part of the small intestine. That is then joining the first part of the colon, known as the cecum. And the ileum is entering the cecum by way of a muscular valve called the ileocecal valve. And when you dissect into the colon next week, you should actually be able to see this ileocecal valve. Often looks like a little pair of lips, kind of puckered lips, poking into the interior of the cecum. The cecum is just basically a big open pouch that eventually leads into the rest of the colon. The appendix is a small dead end pouch that hangs off of the inferior end of the cecum. So food enters the cecum through this ileocecal valve from the ileum into the cecum, and then the food is going to flow superiorly. It's going to flow up towards the head through what's called the ascending colon. The ascending colon is one of these secondary retroperitoneal structures that used to be free moving in the abdomen, but now it's fused to the inside of the abdominal wall on the right side of the body. The ascending colon continues up the right side of the body up to what's called the right colic flexure. It basically refers to a sharp bend, a sharp turn in the colon up here on the right side. It's also referred to as the hepatic flexure because this is actually in contact with the inferior surface of the liver. So the ascending colon makes a sharp turn here at the right colic flexure and turns to become the transverse colon, which travels across the abdomen from right to left. This transverse colon is intraperitoneal. So even though the ascending colon is secondarily retroperitoneal and fused to the abdominal wall, the transverse colon is not. The transverse colon is free to kind of flop around inside the abdomen, free to move around a little bit. And it's anchored to the posterior abdominal wall by a mesentery. Over on the left side of the body, the transverse colon then makes a sharp turn, known as the left colic flexure, also referred to as the splenic flexure, because this is in contact with the spleen. So at that left colic flexure, the colon then turns inferiorly. The food is now flowing inferiorly down through the descending colon. Descending colon is another one of these secondary retroperitoneal structures. It's fused to the inside of the peritoneal cavity on the left side of the body. Descending colon then makes more of a gentle curve to become what's known as the sigmoid colon. Sigmoid colon, sigmoid means S-shaped. And this part, again, is intraperitoneal. So when you see the sigmoid colon in lab today, you'll see that you can actually kind of pick it up and flop it around a little bit. And it is anchored to the posterior wall by a posterior mesentery, just like the rest of the gut. The sigmoid colon then leads down to the rectum, which is deep down inside the pelvic cavity, and then that leads to the anal sphincter and then out through the anus. So the colon has really one primary job, and that is to reabsorb water from the digested food, or what we would call stool at this point. The slide here says absorption of water and concentration of stool, but really that's doing the same thing. As you reabsorb water from the stool becomes more solid and more firm to actually make poop. At least, hopefully, you reabsorb the water to make the poop. Some interesting features that are found on the different parts of the colon. If you look at the interior of the colon, and again, you'll cut into the colon next week sometime, you see that it also has distinctive folds on its inner surface, which are designed to increase the surface area of the mucosa on the inside of the colon to increase the absorption of water. But these folds are not complete circles. They don't go all the way around the inside of the colon. Instead, they form these little sort of half moon shaped ridges on the inside of the colon. So instead of plicae circularis, these are known as plicae semilunaris, the half moon shaped folds. I had an argument about this with my gastroenterologist one time. I was in the midst of a colonoscopy. So she's got a tube 3 feet up my butt, and I decided that I wanted to stay awake for it so I could actually watch it on the video monitor, because I was kind of intrigued by it. And I said, "Oh, those are the plicae semilunaris." And she said, "No, those are plicae circularis." And I said, "No, they're not. They're plicae semilunaris." So I didn't go back to her for a colonoscopy after that, because when a gastroenterologist doesn't know their basic colon anatomy, it does not inspire a lot of confidence. All right, some other features of the colon include these, all these little bulges running along the whole length of the colon are these little pockets called haustra. And internally, these haustra are separated from one another by those semilunar folds. But they just look like little bulges on the outside of the colon. And you definitely don't see these in the small intestine, so they're very distinctive of the colon. Also on the outside of the colon are these 3 bands that run the length of the colon. And you can see one of them labeled up here called taenia coli. And if you were actually able to pick up a segment of the colon and turn it around in 3D, you'd see that there are actually 3 of these taenia coli running the length of the colon. They are muscular bands. These actually represent that outer muscular layer, that longitudinal muscular layer. But instead of that longitudinal muscular layer going all the way around the organ, the way it does in the small intestine and the esophagus, that longitudinal muscular layer is segregated into these 3 narrow bands on the outside of the colon. So these are longitudinal muscles running the length of the colon. It's just that they're divided into these 3 discrete narrow bands. Final structure that you'll see on the outside of the colon that you won't ever see on the small intestine, so they're fairly distinctive of the colon, are things called appendices epiploicae. Sometimes I think the book may use a slightly different term, like the epiploic appendages. They're basically little pouches of fat that hang off of the outer surface of the colon. And people with more body fat are likely to have much larger appendices epiploica, but even skinny cadavers will have some of them typically. So Zooming in on the cecum, you see that ileocecal valve again, in this case, in this Netter painting, really looking like a pair of lips. And then you see the appendix is just this little dead end pouch that hangs off the inferior end of the colon. The appendix is usually illustrated the way you see it in this particular slide, where it looks like this little worm that's dangling off of the inferior end of the cecum. But turns out that actually represents the condition in less than half the population. I think it's only about 30 or 40% of people have what's called, forgetting the word now, drawing a blank. Anyway, 30 or 40% of the population has this type of appendix that hangs off the cecum. Actually, more people have this situation known as a retrocecal appendix, where the appendix ends up getting trapped posterior to the cecum when the ascending colon fuses to the abdominal wall later in development. So remember I said ascending colon is one of these secondary retroperitoneal structures that starts out free floating in the abdomen, but then fuses to the right side of the abdominal wall. And when it does that, it often traps the appendix posteriorly. All right, so that takes us through the entire length of the gut tube, basically from esophagus to anus. But there are these other organs, these accessory organs located within the abdomen, some of which are actual pouches off of the gut tube. Others are not, but they're still closely related to the abdominal organs. So here's the spleen. The spleen does not develop as a pouch off of the gut tube. The spleen is basically like a giant lymph node. It's a large lymphatic organ that develops within the posterior mesentery, essentially right behind the stomach. And in the adult, it lies just a little bit superior and lateral to the stomach on the left side of the body, right up under the dome of the diaphragm. It is covered with mesentery, which is anchoring it to the posterior abdominal wall, just like most of the other abdominal organs. The tail of the pancreas extends over towards the left side of the body, all the way up to actually come in contact with the spleen. And the only connection of the spleen to the rest of the body, really, I mean, besides the mesenteries that cover it, is it's connected by a large artery and a vein. There's a big splenic artery that supplies blood to the spleen, and a big splenic vein that brings deoxygenated blood back from the spleen. And it really does function similar to a lymph node. It's filled with T cells and B cells, which are involved in the immune system. And in some infections, like mononucleosis, people will have significant enlargement of the spleen. It's basically like a swollen lymph node and becomes very, very enlarged in conditions like mono. It also has an additional function that lymph nodes don't have, is that the spleen also helps to remove old red blood cells from circulation and recycle the different components of those red blood cells. So here's what the spleen looks like if you could remove it from the body. At the top is the anterior view, but another term for anterior view would be visceral view. Viscera is another word for the organs in the body. So the visceral view here is referring to the side of the spleen that's facing towards the other organs. And you can see that it actually has indentations where it comes in contact with its neighboring organs. So there's a large gastric surface where the anterior part of the spleen is actually in contact with the fundus of the stomach. There's a renal surface where the spleen's in contact with the left kidney. And then there's a colic surface where the spleen is in contact with the left colic flexure of the colon, known as the splenic flexure of the colon. On this anterior or visceral surface of the spleen is where you find the hilum. Just like the hilum of the lung, it's the point where the vessels enter and exit into the spleen. The posterior surface of the spleen would also be referred to as the diaphragmatic surface, This is just a very broad, smooth, rounded surface that sits right under the dome of the diaphragm on the left side. The liver is a very complicated organ. It's also one of my favorite organs. You'll see in a minute. One of the reasons why it's my favorite is because it just does so darn many things. It really is. I mean, every organ in the body is critical. It's not like you can live without, any organ in the body. But I mean, this one just does so many things. It's really crucial to a lot of our physiological processes. So this is the way you're probably used to seeing the liver depicted in a straight anterior view. It has two lobes, a small left lobe and a much larger right lobe. You notice that Netter has illustrated the diaphragm up here, just this thin muscular sheet that completely covers the surface of the liver. And remember, we've talked about this a couple times, that the liver is tucked way up under the rib cage, especially that right lobe should be completely contained within the rib cage on the right side of the body. These two lobes, the left and right lobes, are separated from one another by a ligament. And the term ligament, I don't know, is a little bit deceptive. It's not really like a ligament that you'd find in the skeletal system. It's not like a ligament that's holding two bones together. It's actually part of the mesentery. This is one of the few remnants of the anterior part of the mesentery that connected all of the abdominal organs to the inside of the anterior abdominal wall. Most of that anterior mesentery, from the liver down to the anus, it has disappeared later in development. But this is one place where that anterior mesentery is still intact. So since this is part of the mesentery, it's actually continuous with the visceral peritoneum that's actually lining the whole surface of the liver. Remember, all of the abdominal organs are going to be covered with a layer of visceral peritoneum. Yeah, Brianna. Yeah, most of it has disappeared in the adult.
And then what still be there like during development or as a baby?
Yeah, I think it disappears late in fetal development. So I think the whole anterior mesentery, except for this falciform ligament and one other part that we'll talk about in a minute, those are the only parts that remain. I think that's true even at birth. I think it's already mostly gone by that point. So when you do your dissection today, the reason that the dissector tells you to cut the linea alba and stay to the left of the umbilicus is because this falciform ligament is attaching to the inside of the linea alba, but just slightly to the right. And in particular, if you look down at the inferior end of the falciform ligament, you find something called the ligamentum teres, which from Latin translates into round ligament. This is actually the remnant of the umbilical vein that brought oxygenated blood from the umbilical cord into the fetus during embryonic development. So in the umbilical cord, there's one great big vein, which is bringing oxygenated blood from the placenta to the baby. And that passes through the umbilicus, through this umbilical vein. And that oxygenated blood coming from the placenta has to go through the liver before it gets back to the heart. So this ligamentum teres is the remnant of that big umbilical vein. And this is attaching to the inside of the umbilicus, again, a little bit to the right. So that's why we keep our cut into the abdomen to the left, so that we don't cut the ligamentum teres or the falciform ligament. Now, eventually you will have to cut them, but you want to actually see them intact first just to recognize them. Right, now this is a view that you may not see very often. This is an inferior view of the liver, also known as a visceral view, because this is the surface, the inferior surface of the liver is what's in contact with all the other organs. So you can see how the inferior surface of the liver is in contact with other organs. So the left lobe, which is over to the left side of the body, has a gastric surface on its inferior aspect. This is in contact with the fundus of the stomach. The right lobe of the liver on the right side of the body has a renal area or renal surface that's in contact with the right kidney, and then a small colic area or colic surface, which is in contact with the right colic flexure or hepatic flexure of the colon. Now, the other thing to notice on here is that the liver does not have just two lobes. It's not just left and right lobes. If you look on the inferior surface, you see that there are two additional, much smaller lobes that are visible only in this view. There's a lobe known as the quadrate lobe, which is basically square in shape. That's where it gets its name from. It's a quadrilateral, four-sided shape. And that's actually sandwiched in between that falciform ligament and where the gallbladder sits, and also lies between the anterior border of the liver, which would be down here at the bottom, and then this area in here known as the porta hepatis, which is essentially like the hilum of the liver, where all the blood vessels and things go in and out. So that four-sided quadrate lobe between gallbladder and falciform ligament. And then there's an even smaller lobe known as the caudate lobe. Caudate is referring to tail. I'm not sure exactly why somebody thought this looked like a tail. To me, it looks more like a tongue. So I'm surprised they didn't call it lingula, since that means tongue in Latin. But it is this little sort of tongue-shaped lobe that sits posterior to that porta hepatis. The porta hepatis, as I said, it's kind of like the hilum of the liver. It's a point where blood vessels are entering the liver. So you've got a hepatic artery, which is bringing deoxygenated blood, or excuse me, hepatic artery bringing oxygenated blood into the liver to actually supply the liver with oxygen. But there's also a great big vein in here called the hepatic portal vein. And we'll talk a lot more about that a little bit later in another lecture. And then the bile ducts where bile is being produced and then fed down into the gallbladder and into the duodenum are poking out of the liver here at this point. So here's why I love the liver so much, because it does all these things. So one really crucial thing to know about the liver is that all of the blood coming from your digestive organs has to pass through the liver before it goes anywhere else, before that blood gets back into the circulation, before it gets back to your heart and gets circulated throughout the body. And this is what that hepatic portal vein is all about that I just pointed out on the previous slide. The hepatic portal vein represents all the veins coming back from the stomach, the spleen, the small intestine, the colon. All of those abdominal organs are sending their deoxygenated blood through a system of veins that all come together to form this big hepatic portal vein, which enters into the liver. And that blood has to pass through the liver and essentially be filtered by the liver before it returns to the heart. So that means that all of the nutrients that are absorbed by your small and large intestines go to the liver first before they go anywhere else in the body. So part of the job of the liver is to extract some of those nutrients, to absorb some of those nutrients coming back from the digestive organs and store them for later. So for example, we talked about this a little bit when we talked about the autonomic nervous system. Glucose that's in the bloodstream that's been absorbed from your digested food is absorbed by the cells of the liver and converted into a molecule called glycogen for storage. And when your body needs glycogen later, there's another process that converts that glycogen back into glucose, and then liver cells dump that glucose back into the bloodstream. But it's the liver that's absorbing glucose, converting it to glycogen, and storing it until you need it. And then it's also the liver that then breaks it, glycogen down and releases it into the bloodstream. The liver is also responsible for absorbing lipids out of the bloodstream. So any fats that you digested are going to pass through the liver first, after coming from the intestines. These fats will pass through the liver, and the liver will absorb cholesterol and other lipids, and then repackage them into things like VLDL, LDL, HDL. So these are your high density lipoproteins, low density lipoproteins, very low density lipoproteins. Basically, they're little packages of lipid and protein in these little balls. And the liver manufactures all of that stuff. And in doing so, it regulates the levels of lipids and cholesterol in your body. Turns out that the liver is just about the most important organ in your body for regulating your blood sugar levels and your lipid and cholesterol levels. I mean, the pancreas is important, obviously, because it produces glucose, which is necessary for the absorption of glucose into your cells. But the liver really is what regulates the level of sugar in your blood, and it regulates the level of lipids and cholesterol in your blood. So there are people who have familial high cholesterol, that just genetically, hereditary, they have high cholesterol. And it's all because of their liver. It makes no difference what they eat. They have familial high cholesterol. The liver also is going to metabolize a lot of the bad stuff that is absorbed from your intestines that has to go through the liver before it goes anywhere else. So the liver is kind of your body's first line of defense against all the alcohol you drink and all of the illegal drugs and things that you do, as well as the legal drugs that you take. One of the tricky things with developing any kind of pharmaceutical is you have to make sure you give somebody enough of a dose that it can bypass the liver and there's still enough left over to do what it's supposed to do. Because the liver doesn't know the difference. All it knows is it sees something foreign. And even if it's a good drug, it's going to destroy some of it and metabolize some of it. So you have to give people sufficient dose that it can get past the defenses of the liver and actually go through the rest of the body to do what it's supposed to do. Similar to the spleen, the liver also filters out old red blood cells from circulation. But then once it does that, the liver does something that I consider really remarkable. It takes the contents of those old red blood cells and recycles them. So the key component of red blood cells is a protein called hemoglobin, which is the protein that actually carries oxygen in the red blood cells. And hemoglobin consists of two parts. There's the globin part, which is basically just protein. So the cells of the liver split the protein part off. They split off the globin and recycle the globin to make new proteins. The other part of hemoglobin is the heme part, which is a ring-shaped structure that contains an iron atom. And the liver removes the iron atom, takes the rest of the heme molecule, and converts it into a chemical called bilirubin, which is the major component of bile. And so the liver is recycling the heme component of hemoglobin from these old red blood cells, converting that heme group into bilirubin to produce bile. The bile is then secreted through a system of ducts. Some of it goes into the gallbladder for storage, but ultimately the bile flows down into the duodenum to help with the digestion of fat. So it's using one old byproduct and recycling it into something new that your body needs to help digest fat. Yeah, Audrey.
So when the spleen, does it do anything with it? Does it send it to the liver, or do it just?
Yeah, a lot of the heme component from the red blood cells that are broken down by the spleen eventually makes its way over to the liver. And I think the spleen itself takes care of the globin part, just recycling the protein component. Okay, so the bile that's produced by the liver is collected by a series of tiny little bile canals. And eventually those little bile canals lead into these two hepatic ducts. So there's a left hepatic duct, which is collecting all of the bile from the left lobe of the liver. And then there's a right hepatic duct collecting all of the bile from the right lobe of the liver. These two hepatic ducts then join to form a common hepatic duct. So left hepatic and right hepatic ducts join together to form a common hepatic duct. So that's carrying all of the bile that's being produced by the liver, out of the liver. That bile is going to flow down through the common hepatic duct. And most of the time, that bile is then going to turn, make a little detour, travel through what's called the cystic duct, which then leads into the gallbladder, which is attached to the visceral surface of the liver. So most of the time, most of your day, as long as you're not eating a fatty meal, there's this slow trickle of bile being produced by the liver, flowing through left and right hepatic ducts, down through the common hepatic duct, and then back into the cystic duct to be stored in the gallbladder. And the job of the gallbladder is to simply store the bile, but also to make the bile more concentrated. The gallbladder actually absorbs water from the bile to make the bile thicker and more concentrated. Then you eat a pizza, and there's a hormone released by your stomach called cholecystokinin that says, hey, we just ate something with a lot of fat in it. We need some bile to help digest this fatty meal. So that causes smooth muscle in the gallbladder to contract, and it squirts the bile back through the cystic duct and now down into what's called the bile duct itself. So the bile duct starts where the common hepatic and cystic ducts join together. But the gallbladder forces the bile back through cystic duct down into the bile duct. The bile duct passes behind the pylorus of the stomach, enters the pancreas. The bile duct is actually embedded within what's called the head of the pancreas. And that bile then ends up passing through something called the major duodenal papilla. I got two names here. There's something called the ampulla of Vater, which is a chamber where the bile duct and the pancreatic duct join. So the little chamber here where the bile duct and pancreatic join, that's called the ampulla of Vater. And then the major duodenal papilla is this thing that looks like a tip of a little finger that protrudes into the duodenum. And there's a little hole in it, a little orifice, and bile then flows into the duodenum where it mixes with your fatty meal to help digest fat. So here you see that same structure just in cross section. So we've got bile produced by the liver flowing through left and right hepatic ducts, down through the common hepatic duct. Most of the time, if you're not eating a fatty meal, that bile is going to then turn and go up the cystic duct into the gallbladder, where it's going to be stored. The gallbladder is going to absorb water from the bile to make it more concentrated. Then when you do eat that fatty meal, this hormone causes the gallbladder to constrict. It squirts the bile back through the cystic duct, now down through the bile duct itself, through the head of the pancreas. The bile duct joins the pancreatic duct to form something called the ampulla of Vater, this little chamber right here. And then from there, the bile flows from the ampulla of Vater through the major duodenal papilla into the interior of the duodenum to help you digest fat. So the pancreas itself is a two-part organ. It's a double organ. It's a gland, but it includes both an exocrine gland and an endocrine gland. So an exocrine gland is any gland that produces something that drains through a duct into, typically into some other organ or into some space. So your salivary glands, for example, produce saliva that drains through ducts into your oral cavity. The exocrine part of the pancreas is what produces very powerful digestive enzymes to help with the digestion of fat and carbohydrate, but especially with the digestion of proteins. So throughout the pancreas, you have cells that are producing these powerful digestive enzymes. These enzymes are all collected by the pancreatic duct. That pancreatic duct then flows and meets the bile duct to form that thing called the ampulla of Vater. And the digestive enzymes then flow into the duodenum And these pancreatic enzymes, like I say, they help with digestion of fat and carbohydrates, but especially they're particularly important in the breakdown of protein. In addition to the main pancreatic duct that joins the bile duct at the ampulla of Vater, usually the pancreas also has a small accessory pancreatic duct that flows through a separate papilla. There's something called the minor duodenal papilla that the accessory pancreatic duct flows through. Now, the other part of the pancreas is an endocrine gland. An endocrine gland is a gland that produces something, typically a hormone, that is then released directly into the bloodstream. There are no ducts that are draining fluid, into some organ or into some space like the mouth. So another good example, or a couple of good examples of endocrine glands would include things like the thyroid gland that doesn't have any ducts at all. The thyroid hormones are just dumped into the bloodstream. The adrenal gland, same thing. So the endocrine part of the pancreas includes the islets of Langerhans. These little clusters of cells that are scattered throughout the pancreas contain A cells and B cells, or alpha and beta cells, that release insulin directly into the bloodstream that assist in the absorption of glucose into your cells, into your body cells. Now, I mentioned earlier that one of the jobs of the gallbladder, besides just storing bile, is to absorb water from the bile to make the bile progressively more concentrated. Well, one downside to that is if you make the bile really concentrated, you can actually begin to develop crystals that will crystallize out of solution in the bile. These little crystals can aggregate together to form little grains of sand, and the grains of sand can in turn aggregate together to form actual stones. And this is how gallstones are formed. Sometimes the gallstones are formed from the bilirubin itself, from the main component of bile. If you have a very fatty diet, very high cholesterol diet, sometimes you can actually get gallstones that are formed from cholesterol crystals instead. I think those are the two main sources of gallstones. These little stones can be very dangerous because they can block different parts of this system of bile ducts and can even block the pancreatic duct if they migrate down into the head of the pancreas. So the simplest situation, one that's actually very common, is that one of these little stones can migrate from the gallbladder into the cystic duct, and if the stone is big enough, it can actually get lodged in the cystic duct and block the cystic duct. So what happens is every time you eat a pizza or any other fatty meal, that hormone goes to the gallbladder and says, okay, gallbladder, do your job, contract, squirt bile into the duodenum because we need to digest this pizza. Well, the gallbladder squeezes, but nothing happens because there's no way for the bile to get out of the gallbladder because of this blockage of the cystic duct. So the gallbladder keeps squeezing and squeezing and squeezing and becomes very irritated, very inflamed, and can be very, very painful, like somebody sticking a knife into your right shoulder. People who have these attacks of gallbladder pain will typically have their gallbladders removed. That's the main reason why people have their gallbladders removed. Now, let's say you've got one of these little stones that migrates through the cystic duct, doesn't get trapped in the cystic duct, but instead makes it through the cystic duct and migrates down into the bile duct. And now it gets trapped in the bile duct. And just to refresh your memory, going back here, if that stone manages to make it through the cystic duct, but get lodged somewhere down here in the bile duct, it's still basically blocking the outflow of bile from the gallbladder. So it may also cause that kind of gallbladder disease, that gallbladder inflammation and pain. But probably more importantly, the stone is also blocking the flow of bile out of the liver. That bile has nowhere to go to get out of the liver. So it causes bile to back up in the liver itself. And that chemical component of bile called bilirubin, since it's got no place to go and it can't get out of the liver, it actually backs up into the bloodstream bilirubin begins to circulate around in the blood, where it deposits specifically in certain tissues: the skin, the sclera of the eyes, the white of the eye, and the brain. This bilirubin is very yellow, and when it deposits in the skin and the sclera of the eye, people look really, really yellow. I've seen photographs of it. It's pretty dramatic. I've never seen it in person myself. I remember my mom had her gallbladder removed, and they didn't realize that she also had a stone that had made its way from the gallbladder into the bile duct. So after her gallbladder removal surgery, my dad came home from work one day and he said that my mom was just bright yellow. And so, I mean, he didn't know exactly what was wrong, but he knew that that's not normal. So he rushed her to the hospital, and she had to have emergency surgery to get the stone out of the bile duct. So this condition is, you probably heard of it, this is called jaundice. Yeah. That's a great question. I know you're right. I mean, a lot of babies are born yellow, a lot of babies are born jaundice. It's not anything to do with a disruption of the bilirubin system. I forget exactly why. And they don't have to have surgery. You just put them under an ultraviolet light. And it gets rid of the bilirubin in their skin. But I forget the specifics of how that works. So having some bilirubin in your skin and in the sclera of your eyes is no big deal. Sure, you're bright yellow, but other than that, it's not going to hurt you. But the brain doesn't like the bilirubin. If it goes on even for a few days, it can cause irreversible brain damage. So if you ever see somebody bright yellow, get them to a hospital right away. The final and probably most dangerous situation is if that little stone makes it through the cystic duct, travels all the way down the bile duct, but gets lodged in the ampulla of Vater, down inside the head of the pancreas. So again, to refresh your memory, if that stone works its way down the cystic duct, through the bile duct down here, and gets stuck in the ampulla of Vater, especially right near the entrance to that major duodenal papilla, you're blocking the whole biliary system, so you could have gallbladder symptoms. You could potentially develop jaundice, but it might never get that bad because this might kill you first. It's blocking the pancreatic duct, and that's bad. Because the pancreatic duct is producing these powerful digestive enzymes that digest carbohydrate, lipid, and especially protein. If you block the outflow of these digestive enzymes from the pancreas will digest itself from the inside out, which will cause damage to the pancreas. It's a condition known as acute pancreatitis. This can lead to hemorrhage of the pancreas, massive blood loss, destruction of the islets of Langerhans cells, so you lose the ability to produce insulin because you've destroyed the pancreas. And these people can often slip into a coma, and about 20% of cases are fatal. Okay, we will come back to this because we're already over time. But I think we'll be able to get caught up next time. So let's stop the share. Oops.